All right, this is our first lesson in Unit 3, the periodic table. I think that we probably just did a look back, so that's the announcements, and the Unit 2 exam item analysis, that would be the look back. All right, so the do now is list 3 things you can find about each element on the periodic table. What is atomic number? How can you identify it on the periodic table? And what is atomic mass? So I want you to take these 3 questions and write them on a separate piece of paper and put it under the classwork section of your binder. We will do those in class tomorrow, and make sure you have the date on there as well. So the mini lesson, what are the common names of the following groups? All right, so group 1, I am talking about this column all the way on the left. That's called group 1. And then the column beside it would be called group 2. Group 17 is all the way on the right. It's I guess that's indigo. And then the magenta column is group 18. Those are the ones that matter the most, I suppose, in the way, especially in that they have English names as well as just a number. Group 1 we call the alkali metals. Group 2 we call the alkaline earth metals. Group 17 are called halogens. Group 18 are called noble gases. All right, why do you think that the group 18 elements are referred to as monatomic gases? So monatomic is another name along with noble. I'll go ahead and write the others in as well. So sometimes they're called monatomic gases. And actually sometimes they're referred to as inert gases. So to answer question number 1, why are they referred to as monatomic? Mono would mean one and atomic would mean atom. So a one atom gas is one that does not bond. And the doesn't bonding part, it dovetails really nicely with inert and the fact that they're noble, meaning that they don't interact with other atoms, they don't bond to them. All right, number 2, what do elements within the same group have in common? So I chose elements here that are all in the same group. I chose lithium, sodium, potassium, and rubidium, and I believe that would be, let's see, lithium, sodium, potassium, and rubidium, I believe. So I'm just choosing these 4 elements. And the question is, what do they have in common? So I put in some data here to help you see that, but what they do have in common is they have the same ion charge. So elements going down a group have the same ion charge. And although they do have different numbers of electrons in the orbitals, like this one has 2 orbitals, this one has 3 orbitals, 4 orbitals, and 5 orbitals. Although they do have different numbers of orbitals, in the very last orbital, right here, they all have 1 electron, which matches up nicely with the ion charge. So I'll summarize that now. So I just said that they have the same number of electrons in the last orbital, and they have the same ion charge. And by the way, the value for both of those is +1. Now, what do elements within the same group not have in common? I don't know if you can remember what that chart said, but they did not have the same number of orbitals. We refer to periods by their number only. So the periods don't have any English names to go with the numbers. So period is it's like a row, and I'm numbering them for you now. You just number from the top, starting with 1. Okay, so number 5, what do elements in the same period have in common? So let's use this data table. I chose lithium, beryllium, boron, and carbon, which would be the following elements. There's lithium, beryllium, here's boron, and there's carbon. So I'm just going across the period or across the row. And the question reads, what do elements in the same period have in common? So let's check out the data table for those elements to make sure. While their electron configurations are different, they do have the same number of orbitals. They each have 2 orbitals in that in period 2. And I rewrote that here. How can you tell how many orbitals an element has? I'm not sure if you noticed this just now, but these elements were all in period 2, meaning they were all right here in this second row. So all those elements were in period 2, and they all had 2 orbitals. So the number of the period should match the number of orbitals. So what do elements in the same period not have in common? You can see pretty easily that they all have different ion charges. So in the next question, this is a very important question. It says, how are the elements on the periodic table arranged? They're arranged by atomic number, which is the number of protons. While you will see some patterns that look like the atomic mass is the way that they've been arranged, you'll also see breaks in that pattern. So it's actually just atomic number that determines where the element goes on the table. So speaking of atomic mass, what is atomic mass? Atomic mass is the weighted average mass of all the naturally occurring isotopes of an element. All right, so a trend. A trend is a pattern. And we're going to look at trends on the periodic table. So for instance, which series of elements does not tend to follow the trend of increasing atomic mass? The series of elements that do not follow the trend of increasing atomic mass are called the transition metals. And let's see, they are here. So inside the red box there, those are my transition metals. They tend not to increase the trend, or they tend not to follow the trend of increasing atomic mass. I believe there are a couple of exceptions right in this area, and you'll be able to find some elements that when you're going from left to right that the mass might go down slightly. In 12 and 13, it asked about metallic character going up and going down. So what I would ask you to consider is that your metals are all over here in this part of the table, and we have nonmetals up here. So nonmetals in the top right and metals in the bottom left. And that actually will give you the answer to this question, which says metallic character increases as you move blank and blank. So if metals are on the bottom left, then metallic character would increase as you move both down and left. But metallic character would decrease as you move towards the nonmetals. So nonmetals were up here. So that's in the top right of the table. Therefore, metallic character would decrease as you move up and right on the table. So if you're looking at the table and you want to know which element is absolutely the most metallic, it's going to be the one that's farthest to the left and also farthest down on the table. And that element is capital F. And when you look it up on table table S, it'll be called francium. All right, where are nonmetals located on the periodic table? So I mentioned it earlier, but nonmetals are on the top right of the periodic table. So nonmetals are on the top right. Some of their properties, I will list them in blue and then I'll discuss. So I said that they could be S, L, or G, so solid, liquid, or gas. which is unique because metals typically are solids. So non-metals can be any of these three things, solid, liquid, or gas. There are good examples of all of them. But if they are solid, if you're looking at one that is a solid, it'll have a low melting point. So when I write MP, I mean melting point. So if solid, low melting point. So they're easy to turn into a liquid. And if solid, they'll be brittle, meaning that if you tried to bend it or if you struck it with a hammer, that it would snap or break. That's what brittle means. So if solid, they tend to be brittle. They're also very poor conductors of all kinds of energy, whether that's heat or electricity. And they're dull, meaning that they are not shiny. So they'll be dull when you look at them. And when we're looking for metals on the periodic table, we'll find metals on the bottom left. And I'll write in some of their properties in blue, and then I'll discuss. So I actually just sort of wrote the opposite of a lot of the things that I wrote for nonmetals. And metals and nonmetals are opposites in many ways. So in any case, I said that almost all metals are solid, and I did give one exception. And this is an exception that you are responsible for memorizing before the Regents. And the exception is Hg, which is the symbol that we use for mercury, and it's a liquid at room temperature. So it's a liquid at room temperature. If the metals are solid, and almost all of them are, then they'll have high melting points. And these are probably two new words for you. I'll zoom in for them. Malleable and ductile. Malleable is a word that we use with metals a lot, and so is ductile. Malleable means that you can be pounded into a thin sheet, like a piece of foil, for instance, and it comes from the Latin mallet, meaning like a hammer. And then ductile also comes from Latin. Duct is like a pipe or a conduit, this means they can be pulled into a thin wire. So metals can be pounded into a sheet, and metals can be pulled into a thin wire. All right, also metals are good conductors of heat and electricity, and they are shiny. And one more word that we can use instead of shiny that you'll probably see on the Regents is lustrous. So lustrous means shiny, it means it has a lot of shine to it. All right, 17, where are metalloids located on the periodic table? So metalloids border the staircase. So the staircase I'm referring to is here in this sketch. So it's just right here. And a metalloid is an element that has some properties of metals and some properties of nonmetals, but you'll find them right here to the right of the staircase and right here to the left of the staircase. So they just need to border the staircase. A corner border doesn't count. So like let's say that this is the staircase. And then these are the elements. So I'm going to make this line really bold so that you know that that's the staircase. Here are some elements. This one's a metalloid. This one would be a metalloid. This one, not a metalloid. It only shares a corner with the staircase. So if it just shares a corner, that's not enough. But in any case, all the elements that border the staircase are metalloids except for aluminum, polonium, and astatine. If you're looking for aluminum, you will find it about right there on the staircase, and it is definitely a metal, so it doesn't count as a metalloid. And then polonium you'll find down here at the very bottom of the staircase to the left of it, and we would count it as a metal. And astatine, AT, you'll find down here to the right of the staircase, and we would call it a non-metal. Properties of metalloids are going to be half properties of metals and half properties of nonmetals, meaning that instead of being conductive, they'll be semiconductive, so they'll have some ability to conduct energy. Instead of being dull, they'll be somewhere in between shiny and dull. And all the other properties that we listed between metals and nonmetals, those properties will be somewhere in the middle. So the one that I wanted to point out here and highlight especially is semiconducting. So that means that they can sort of half conduct. And this is really important because all the computer chips that we use to power our cell phones, to power our laptops, to power our iPads and our desktops, all of those computers rely on semiconductors, and specifically they rely on a very specific semiconductor called silicon. And you'll find it on your periodic table. It's element number 14. And since it lies on the staircase, since it borders the staircase, like these two elements, then we also know that it has some of the properties of metals and some properties of nonmetals. And the one that it has that matters a lot is that it's a semiconductor, which means that we can use it to make computer chips. And lastly, the last question for you is, what are transition metals? And I actually highlighted them earlier in the lesson, but in my sketch, they would be here in this large block in the middle between the two high points. So transition metals are metals that tend to defy our normal rules for how elements, become ions and how they behave and how many electrons they gain or lose. So these are metals that don't follow all the rules. Typically, the Regents won't ask you a lot of specific questions about transition metals for that reason. But we need to know what they are, and we need to know where we can locate them. So generally, I would just say transition metals are from groups 3 to 12. So once you get to group 13, I believe group 13 starts right about here at the staircase. So once you get to group 13, generally we're going to consider those all nonmetals. But somewhere in between group 3 and group 12, so that's group 3, this is group 12, those will all be considered transition metals. All right, and to finish up, I want you to copy down these summary questions in your notes, and that'll be right after the do now questions that you just copied down, and they should both be copied down on the same page, and they'll both be filed under classwork in your binder. The notes that you took for this lesson will be filed under notes in your binder, and make sure everything has a date.